What is up, you math maniacs? This is section 3.3, day 3, analyzing graphs of quadratic functions. And the application here is going to be basically write your function for your unknowns with lots of variables, and then use the information to turn it into a function with just one variable, and then find the max and min of a function. So again, we're not solving, we are finding the maximum. Let me show you what I mean. You're going to have knowns and unknowns, and then you're going to eventually get down to just this one equation, not a equals w times L, but a equals w times 12 minus 2w. Just w's on the one side. And this is something you can plug into Desmos and find the maximum of. Here, one equation with two unknowns, s and t, and then you're going to find the maximum of it, and the maximum is going to be the answer. So let's talk about it. Example 1, maximizing area. A landscaper has enough bricks to enclose a rectangular flower box below the picture window of the Jacobson's house with 12 feet of brick wall. And you can see the 12 feet right here. It's going to be this rectangular box, and the picture is actually inaccurate because you can see that the brick extends here along this edge in the picture, but that's not what we want to do. We just want to make brick, 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 and those three sides are going to be a total of 12. If the house forms one side of the rectangle, what is the maximum area the landscaper can enclose? What dimensions of the flower box will yield this area? So I drew a picture, width, length, and the fourth side is just going to be the house. And so we know that width plus length is equal to 12, and we know that the area of the box is going to equal w times L. I'm trying to find a maximum of area, like under what conditions will area be the greatest, and I don't know what L and W are to make that happen. So what I did was I took width plus length equals 12, and I solved it for length so that I could use that expression here. The area is no longer width times length. It's going to be area is equal to width times what length is equal to. Length is equal to 12 minus 2w, so I just made the substitution here. Length is equal to this, so I just put it in. And now I have a function that I can maximize. It has just one variable, and I can figure out where the peak of that function is. It's a little easier for me to do it by hand if we distribute first. A is equal to negative 2w squared plus 12w, and so a is equal to negative 2. As you can see here, a is negative 2, b is equal to 12, and there's no c term here, so c is equal to 0. The formula negative b over 2a yields that yields w is equal to 3 feet. That's where the line of symmetry is going to be. The maximum is going to be, if you draw the parabola, the maximum is going to be along the line of symmetry at the value of negative b over 2a, and that's where width is equal to 3 feet. Plug that in to our equation that has w and L, I can figure out that the length is going to be 6 feet. So 3 feet times 6 feet is going to be 18 feet squared when you're trying to find the area. And we can verify that graphically. Next, the height of a rocket. A model rocket is launched with an initial velocity of 100 feet per second, as you can see in yellow, from the top of a hill that is 20 feet high. Its height in feet, t seconds after it has been launched, is given by the function s of t. So 100 comes from the fact that that's how quickly it is launched from the top of the hill at 100 feet per second. 20 is how high the hill is, that's your starting height. And negative 16 comes from the fact that we're measuring it in feet, and we're standing on Earth. Earth is this, the gravity is this strong, pulling it downward all the time. That's what the negative is there for. Negative indicates pulling down a downward motion. So if we were standing on Jupiter or the moon, this number would be different, but because Earth's gravity is just this strong, then we're going to use negative 16 feet per second squared here. So let's maximize that. We see that the a value is negative 16, b is equal to 100, c is equal to 20. You can see that t is going to have a maximum at negative b over 2a, which simplifies to this, 3.125 seconds. That's actually a lot faster than graphing it. And if you plug t into the original function, you'll see that s of t is going to be equal, s of 3.125 is equal to negative 16 times 3.125 plus 100 times 3.125 plus 20. This is just plugging it into the original function. S of 3.125 is 176.25 feet. And we can verify that graphically. At the end of the day, you're going to have to be able to perform the algebra and also perform the task of graphing it, and they should be able to mutually agree on each other, like independently. You should be able to do both methods for finding the maximum, both the algebraics and also the graphical part. Example 3, finding the depth of a well. 2 seconds after a stone has been dropped into a well, a splash is heard. The speed of sound is 1100 feet per second, and the equation for dropped objects is s equals 16t squared, where t is the time and s the distance. How far is the top of the well from the water? Just for this particular equation, problem example, I'm going to change it from s. We're not going to use s, we're going to use d. So let's just talk about the mechanics of what's going on in this problem a little bit. A coin is going to start up here, and it's going to start out slow, but as anything is when it's dropped. And then as it gets further and further along, it's going to get faster and faster and faster. It accelerates. The equation for acceleration is dictated right here. The distance that you are going to be is going to be equal to 16 times t squared. However, the sound that's going up is going to travel at a constant rate. That's just sound traveling through the air. D is equal to the rate of sound times time. The interesting thing is that we're going to be accelerating here and going at a constant rate here over the same distance. There's only one d. The same distance going down is the same distance going up. The one thing that we know is that 2 seconds elapse from here all the way up to here. That's exactly 2.0 seconds in length. So now that we understand the problem just a little bit, here's the strategy. We're going to write the overarching equation, and we're going to use other equations to substitute for the unknown. What don't we know? What we really want to know at the end of the day is the distance. The first part of the strategy is here. We want to write the overarching equation, which is t1 plus t2 is equal to 2 seconds. That's what we know. That's the overall story is told right here. T1 plus t2 is equal to 2 seconds. And then we're going to change these t1 and t2s into the one unknown, which is d. So we're going to write t1 as an expression of d and t2 as an expression of d, and we're going to solve. The knowns, just to recap, is that the rate of sound, the speed of sound, is 1100 feet per second. The distance, the equation that governs distance traveled down is equal to 16t1 squared. That's the time of the first part of the journey. But going back up, the equation that governs the sound is going to be d is equal to rate of sound times t2. The amount of time it takes for the sound to travel up times the rate of sound. The second part of the strategy is to rewrite these equations so that they're in terms of d. For the t1 equation, we divide both sides by 16, we take the square root, and we get the square root of d over 16 is equal to t1. That's what t1 is. If you know the d, you can divide it by 16 and take the square root, and that'll be the time. Over here, we start off substituting 1100. This d is equal to 1100 times t2. And then dividing both sides by 1100, we get this. D over 1100 is equal to t2. We're going to take these equations, these expressions, and use them back in the overarching equation here. Now we just have to solve. The most complicated part is arriving here, and once we do that, then the actual algebra is not too bad, although we still have to go through it. Simplifying here, the square root of 16, the square root of d over the square root of 16 is just going to be 4, because the square root of 16 is 4 here. Then let's just clear the fraction at this point. That's going to be the most difficult thing. To do that, we have to multiply by the least common denominator, which is 1100. So that means you multiply this by 1100 to get d, 2 by 1100 to get 2200, and this by 1100 to get 1100 divided by 4, which is 275. And because I know that this is going to eventually turn into a quadratic equation, I can solve everything for 0, put everything on the left-hand side, and make a u substitution. Here, this looks like a quadratic equation. It would be the a term, the b term, the c term equals 0. But that's only true if I make the u substitution. If I let u is equal to the square root of d, then that would make a u right here, and then u squared is d over here. So we've got u squared plus 275u minus 2200 equals 0, and so the a values, the a, b, and c values are 1, 275, and negative 2200. So you can see here, using the quadratic formula, x equals negative b plus or minus the square root, all that stuff is here. And I'm only going to choose to examine the positive square root because if we do the negative, then it'll give us a negative value, and that's not going to work in our real-world problem. But if you simplify all that with a calculator, you get 7.780. That's what u is. And you remember u is also the square root of d. So back substituting to try and figure out what d is, we have the square root of d is equal to 7.780. Or when you square both sides, you get 60.5 feet. And that is the final answer. Alright kiddies, it's play at home time with Desmos. What that means is when I do something on Desmos, you do it too. Make sure you can show me your saved Desmos graphs when you arrive in class tomorrow. As you can see, I typed in the equation and we found its maximum at a width of 6 feet and a total area of 36 feet squared. Typing in this equation here, oops, forgot the negative. Makes a big difference because now you can maximize it. Here you can see the very top of the parabola is 3.125 seconds at a height of 176.25 feet. And here there's nothing to maximize because we have the equation square root of d over 16 plus d over 1100 is equal to 2. What's the problem, Desmos? It says we only support implicit equations of x and y. Alright, well, let's change this to x. Let's change this to x. Let's see what happens. Is this really solid green line? What's the value of this green line? It's not telling us. So why don't we change this to y and let y equal 2? Because that's the value that we want y to be. We want to know where is this curve going to intersect? When is it going to have a value of 2? You can see right here. There it is. 60.527, a well of 60.527 feet is going to have a time of 2 seconds exactly. So go ahead and begin 3C3, do the first problem, and copy the problem list